1 second. Yeah, how does it? It's not in full screen, right?
Yes, sir. No, yeah, it started, yeah.
What should I do with full screen now? Again, I have this trouble.
I think in the bottom you have this button to make it.
Yeah, correct.
Yes, exactly.
Okay, so good afternoon. So today is the key lecture of this course, right? If you understood this, that means I have conveyed the message. So neural networks, artificial neural networks, whatever way you want to call them, okay? So we either call it as, so you just say NN or there is a reason behind the use of the word, the letter A, which we'll see in a short while, okay? So thanks to my PhD scholar, Baki Harish, who just submitted his thesis for the help in the slide preparation. It's a very tricky and very slippery topic. As you'll see today that it is quite involved, and though it looks like elementary algebra, the understanding this neural network can be very slippery, and teaching it will be even more slippery. So I'll do my best, but I think the best thing for you would be to follow the lecture, and if possible do some hand calculations along with me. Then you go and revise the lecture and check whether whatever I have done is okay or not, and this is the best way to learn it by yourself, okay? I mean, after you have listened to this lecture, all right? And also thank Baki Harish for the patience he displayed. Okay, every day I'll make at least 10 calls to him, so he has the habit of recording the call so that he doesn't miss any point. So just looking at my mobile, I think I've called him 10 times, the number of times I called my wife. so I think that you can see in the lecture. So we have done our best to make the lecture, as detailed as possible. All right. Okay. Let's start with an introduction to neural network. The origins of the word neural network. Why did they start? So this is something in basically computational statistics, and they want to fit some, and they want to see how input variables and output variables can be related. So why did the term neural network arise? The origins of the term neural network can be guessed to the early efforts or early attempts to find mathematical representations of the way in which information is processed in biological systems. Okay, how do biological systems process information? I keep giving this example of we crossing the road and all that. Okay, so if you are able to come up with an architecture, if you're able to come out with a construct, a mathematical construct, and then you're able to exploit the relationship and use your math to crack this problem, this is the inspiration. Okay, so you look at biological system and see the way the brain processes. Okay, so examples of these are legion. See, for example, the brilliant book by Christopher Bishop. It is available in the campus bookstore. I bought it. So if you really want to do some serious stuff, it's very expensive. It's about 6K. But I think you may get some cheaper versions of this on Amazon. So if you're lucky, you can get it even for 2K or something or so on. But this 6K is very good print with color pictures and all that. So this is a benchmark, right? So if somebody wants to do serious work in neural network, pattern recognition, whatever, Bayesian learning, you must pick a copy of this and keep it. Okay, not just keep it, so keep using it.
Forward. So before you
as
move
of date,
forward,
neural networks have been used in many fields and continue to evolve, even though the claims of some about the biological possibilities are open to question. That is why these biological, so there are two groups of people some people who feel that independently without any reference to biology, we can develop this. Some people feel that there is inspiration coming from biology and so on. So be that as it may, okay, let's leave it at that. Be that as it may, it is safe to, so it would be a much safer proposition to view neural network as a key tool in machine learning. Please note that neural network is not machine learning. Machine learning is many things, and machine learning is not artificial intelligence. Artificial intelligence is, you're talking about a strong AI. People are talking about a strong AI where you can mimic human behavior, but we are nowhere there. Okay, so we are still working only with weak AI. So AI is the superset. Out of this is ML. Out of this neural network, and then in neural network there is a special portion called deep learning or deep neural networks, which everybody is everybody is fascinated about. The other hot topic is basically reinforcement learning, right? Okay, reinforcement learning. So all these are concurrency, recursive neural, recurrent neural network, convolution neural network, and CNN, RNN, and so on. Okay. All right.
Sir,
The work cause of
sir,
yeah.
could you mute Naveen? Could you mute Naveen, sir, please?
1 second. Naveen, can you mute yourself? No, is it okay?
Yes, sir. Now it is okay.
Is it?
Thank you, sir.
Okay. The workhorse of the neural network is the multi-layer perceptron, okay, which is shown on the right side. So what is shown on the right side? This. So much so, many people think that multi-layer perceptron is neural network. I mean, it is not so. They are not one and the same. But it is a workhorse of the neural network, okay, which we'll discuss at length in this lecture. So the basic model consists of multiple layers. See the view graph on the right side. Multiple layers with logistic or linear and other regression models. So there is a bunch of inputs. There's a bunch of outputs. They are all connected through various layers in which what is flowing along all this is basically information is flowing. Information in the hidden layers, you've got some intermediate points and which the information is processed in a particular way and it is stored. If you ask me what is the physical variable, no, we can't explain. But these are the intermediary units in processing this, and finally a combination of all this is again led finally to the output layer. So coming again, there is an input layer which there are many variables. There is an output layer where there could be many variables. There could also be decision of 0 and 1, which is the classification problem which you have seen in the basic. So where you judge yes or no, I will cross the road, I will not cross the road. It will rain, it will not rain. Okay. IPL match, CSK will win or CSK will not win. Suppose you come out with this thing. Stock market, it'll barrier, it won't cross a circuit barrier. There is something called softmax regression, which I didn't have time. There's something called softmax. Okay. So what it does is, okay, it's not apart from. Apart from 0 and 1, there are many classes. For example, let us say that there is a lot of inputs and the output is basically a Likert scale, right? Okay, you all do a teacher evaluation, right? Course evaluation. The Likert scale is a 5-point scale. The teacher covered all the fundamentals very, very well. Okay, your response: agree strongly, agree, neutral, disagree, disagree, strongly disagree. So there are 5 classes here. Instead of saying I will cross the road, I won't cross the road, 0 and 1, there are 5 classes. These 5 classes can be given some points and so on and so. If you have multiple classes and apart from go and no go, there's something called softmax regression. People who are interested in solving problems, these basically come in social sciences. Huh? Social sciences. Okay, market survey. Or you want to evaluate all the what are the various stressors because of working from home during the corona pandemic, COVID pandemic. So you just run a sample, you run a survey, and then you put a Likert scale and all this. Then you can use basically softmax regression to get there. Okay. Now let's get back to this. So the multi-layer perceptron is a model which actually consists of multiple layers with logistic or linear or other regression models. What is the downside? The downside is the heavy use of computing resources, where if you want to use the multi-layer perceptron, even so, the above which is typically used in there is heavy use of computational resources in what we call as the training phase. You want to train the neural network. That is, you please remember the definition of machine learning is a machine gives an improved performance in a task P, in a task as measured by a performance metric P, if it gains from experience. That experience E is basically it is seeing more and more data. Okay. However, this is well worth the effort, as the final product is a compact model. The final product of the neural network is a compact model. It is super duper fast. It's absolutely fast at processing new data. Once a properly trained neural network is available, he or she is a master at prediction. Of course, you can catch me say what will happen if it is extrapolation, this thing, whatever. For extreme things, it cannot do that, but people are still attempting. But generally, if the extremes are already there in your data, in your training data set, then the neural network is unbeatable. It is very fast. Okay. So neural network. Okay. Let us start with some notation and let's start with some. Let's start discussing. Let's go a little deep now. Many database models exist, and the NNs are among the most flexible and universal ones. Now I've deliberately we have put neural network in a black color so that for now you may treat it as black box. The goal of this lecture is to remove the black and make it white so that it is very clear to you what a neural net is. So many people think it is mumbo jumbo, it is some magic. There is nothing like that. It is perfectly derivable. It is mathematically sound. It has got philosophical underpinnings. Everything is available. Set of inputs x. Now your is y. Given x, w, you will get the y. Okay. So the neural network will tell you. So once you fix the weights, okay, which basically come out of the training of the neural. Am I audible? Is it okay?
Sir, you are audible, sir.
Yes,
Yeah, because it says my internet connection is unstable. Okay. I hope things work out fine. Okay. Now, once you fix the weights based on the training the network, if you give a set of inputs x, it will give y. X can be a vector. Okay, x need not be only one x, x1 to x, and y also can be a vector, y1 to yn, whatever. Let us consider a linear model. So now watch carefully. Now the music starts now. The first 10 minutes it was just blah blah. It was all nice, but now the music is. Let's go deep into the neural network now. Let us consider a linear model. The NN for this can be represented as there is a bias unit called x, not the bias. Obviously, you know what bias is. So there are two inputs actually, 1 and x. So please note that this is a technique or a trick which is adopted in ML. So even bias is considered as an input with x equal to 1. Okay. First thing you're learning today, which you have not learned in any statistics or math courses. The bias is an input with x equal to 1. Now the bias, so from 1 there is a arrow which goes up to the sigma. The output is basically the blue color sigma, which returns the value of sigma or the y, given the value of x. Okay, the bias is there. Okay, now the output is written cleverly as w0 x0 plus w1 x1, so that I can write y hat. Y hat is my proposal. Y hat can be written as sigma I equal to 0 to 1 wi xi. Please note that if I equal to 0, with the understanding that x not equal to 1. Okay. So when you actually program it, there is an understanding that x not equal to 1. So never forget the bias unit. Okay. Therefore, the proposal can be put as a linear combination of weights multiplied by the respective values of the variable. So this is the first proposal. This is how you beat it. Any complex nonlinearity, you beat it by doing this. Sir, can all such things, can all sorts of nonlinear function be represented by this? Of course. But what we do is we get into deep learning. What do we do in deep learning? We put it into several layers, and each of these layers we have multiple combinations of linear combinations. Each of these can ride even a logistic function, a nonlinear training function, and so on. Then it is even nonlinear relationships can be captured. Now,
sir, your presentation got stopped, sir.
Why?
You have to restart, I guess, presentation.
Why? I don't know. I hope it
got at one slide only.
Okay. I think, I think I'm using the. Now is it okay? 1 second. I know why it happened. I was using the wireless. Now is it okay? Did you get it, Baki? Hello?
Linear model we got, sir. Linear model.
Yeah. So you can see me, you can hear me.
Yes, sir. I can see you, I can hear you, sir.
Okay. All right. Now let us go down further. Okay. Now So this is basically typical architecture. This is called the architecture. Okay. What is the typical architecture of a neural network? A NN or an ANN has an input layer, one output layer, and one or more hidden layers. Okay. A neuron, which is given by A, which is the maroon circle, is basically it can have a linear or a non-linear operator. The non-linear operator is basically this, for example, G of Z. Okay, G of Z equal to 1 by 1 plus e to the power of minus Z. So this is basically the logistic. Okay, or you can have a tan hyperbolic. Okay, you can have a tan hyperbolic. You can have a rectified linear unit. There are many functions which are possible. Now, the blue is basically the output, the orange is the input, and the maroon is basically the neuron. Okay. Now, in the above example, in the above architecture, there are 3 inputs in one input layer. There are 2 outputs in one output layer, and there is one hidden layer with 4 circles which are called neurons. So basically, there are 4 neurons of maroon color, for 3 inputs orange color, and 2 outputs which are in blue color. And traditionally in the neural network terminology, we put the proposal as Y hat, because Y is for data. Y is for data. So basically, many of you have already done regression will know that the goal is to make this Y bar minus Y whole square. Okay, if it is something like that. So I equal to 1 to N equal to S. So somewhere you have to minimize. What is the fun in minimizing? We minimize in order that we get the W's. So this is called the neural network training. So I broke the suspense much earlier than I expected. All right. So please have it at the back of your mind. So whenever you're working in neural network, you're writing a paper, proposal, you're presenting results. First, you have to declare what your architecture is. This is called one hidden layer. You can also have 2 hidden layers. Now, from every neuron, there is a connection to all the inputs and the outputs. Please see. Now you can see the number of lines which are crisscrossing each other. Each of these lines carries a weight which is given by the W. So now we don't know what the weights W are. The challenge before us is to be able to calculate the weights of all the crisscrossing lines, such that when you do a weighted combination of, if you put a weighted combination of all these inputs, given all the 3 orange values, you should be able to get the blue values. So that is a challenge before you. What is the fuel for doing this? The fuel for doing this is data. That is why you need to have good data. You have to do data cleaning, data preparation, all that. So data science always precedes machine learning. So you do data science, you understand your data very well, look at the patterns, remove covariances, remove correlated variables, make the data very pakka, and then clearly establish that there is some causality. Okay. Once the causality is established, then you come out with an architecture like this, and then now you do deep diving. Okay. You do deep diving and get into the business of neural networks. All right. Okay. Now the sigmoid function. So you can have a nonlinear activation function or a linear activation function. The sigmoid function, the logistic function, is one of the nonlinear operators commonly used in machine learning. We saw this function before, but however, there are some problems with this when it is used for all classes. It is not a one shoe size fits all. Okay, because you can see that it heads towards the saturation beyond a certain value of x. Therefore, it will not distinguish if the values of x keep on increasing. So there is a saturation problem, there is a differentiation problem at some limits and so on. So people are using other types of training functions. The other activation function used in machine learning can be tan hyperbolic, rectified linear unit. There are also other things which are being used. For example, softmax. I already told you softmax is basically similar to logistic, but there are multiple classes from 0 to 1. And rectified linear unit where it's basically a rectified output. Okay, the rectified. So where are these things used? The sigmoid function, logistic function, since it returns only 0 and 1 for all possible values of x, the sigmoidal function is invariably used in a classification problem. You want to classify. Okay, you want to classify. Okay, then basically use the sigmoid function. Okay, softmax is also used for classification. There are multiple. If there are multiple classes. Okay. Now, the tan hyperbolic is mostly used for natural language processing. Okay. And in speech recognition software, how does it recognize? Alexa, play a song from RRR. Suppose you say, Alexa, play a song from Swadesh. How does it recognize? So there is some neural network which is machine learning is going on. It is already machine learned. So probably TANH is used in those places. Nowadays for computational neuroscience, computer vision, speech and all that, the rectified linear unit is a very important tool for the computer science. Okay. So don't think that sir taught us logistics. So for all problems, I'll use logistic. No. Okay. There is a joke in English, right? If what you have is a hammer, everything looks like a nail. It should not be like that. So please choose the appropriate training function, the activation function, depending upon the problem. All right. Now, types of neural networks. Whatever we have seeing on the left side is already I've talked before. This is called a shallow network. A shallow network has got one hidden layer. Hidden layer is basically a collection of neurons which are in maroon color. Okay, they may not represent a physical quantity, but they are some intermediate quantities which are connecting the inputs and the outputs. Okay. Now the deep network involves more than one neural network, more than one hidden layer. All right. So in a problem, sir, how many hidden layers should be there? There is a theorem which says that even one is sufficient. More than two, I think more than two hidden layers are not required unless it is a very, very tough nonlinearity is there and so on. Also, once you have more and more hidden layers, more and more neurons, the number of arrows crisscrossing each other will be too many. For each of these, you have to put a weight, and getting the weights will be a nightmare. It will be overfitting problem. So you'll suffer from what is called the curse of dimensionality. So you have to worry about that. There could be overfitting and so on. All right. So for starters, if the problem is not so tough, stay with one hidden layer. At max, go to two hidden layers. All right. There is a universal approximation theorem in machine learning, in neural network, which says that given sufficient data on neurons, a neural network with even a single hidden layer can approximate any function to any desired accuracy. But the big question mark there is, given sufficient data on neurons. What do you mean by sufficient data? That we'll have to, it may vary from problem to problem, but this is a well-cited paper in basically IEEE transaction on the neural network. These guys are the first to start out with. It appeared in 1999. If somebody wants to go deeper into this, please take a look at this reference where they first proposed the universal approximation theorem. Okay. Now let us go into the Newman neural network nomenclature. So Z is basically linear. Okay, we are talking about, then G is a nonlinear activation function. So Z from Z you go to G. G is operating on Z. Z will be a linear combination of all the weights. Okay, and the X values. Okay, if it is the first layer. So you first calculate the value of Z. G is operating on the Z. From that you will get what is the value of the neuron. So A12, A subscript 1, superscript 2 means what? Superscript 2 means the layer 2. Subscript 1 means the neuron index. So this is the nomenclature followed. Now come down. So there is a input layer X2. There is a weight W21 superscript 1, and it goes to A12. Okay. Now please note that we are introducing many things here. First is basically the activation function. The right side, we are talking about the neurons, which are defined, which are denoted by A, and then there is a superscript and a subscript. Then there is a weight. The weight is written as, for example, W21 superscript 1 means it is connecting from layer 1, the superscript. The bottom 21 means the first number represents the input neuron index, and the second number represents the target neuron. Okay, so the first represents the input neuron, the second represents the target neuron. As we go along, it will become clear to you. All right. Now, the hidden layer, okay. Okay, the hidden layer 1 is considered to be the second layer in a neural network, since the first layer is considered to be the input layer. The first layer is always considered to be the input layer, and the hidden layer 1 is supposed to be the second layer. The hidden layer 2 in this case is the third layer, and the blue color is the output layer. So it's a 4-layer network, and there are two inputs X1 and X2. There is one input which is Y. Now The black ones, 1, 1, 1 are the bias units, are the bias. We don't forget the bias. Okay. Now you can put all the arrows. So you can see that to reach the state A12, so what you do is that A12, that neuron, A12 neuron gets the input from the first bias unit on the first layer. So the weight for that will be W01 superscript 1. Okay. It also gets the information from the first orange neuron X1. So that information is given by the weight W11 superscript 1. Then come down. The input coming from the orange color neuron X2 to the maroon color orange color neuron X2 to the input layer to the maroon color neuron A12 is W21 superscript 1. Okay. As yet, all of these are unknown. The challenge is to find them. Now, like that, you can see that for the let's go to A13. Okay. Am I audible? Is everything fine, Baki?
Yes, sir. You are audible, sir. Please
okay.
go on,
Let's
yes,
proceed. Sir. Let's proceed. Let's proceed. Now, let us say that I want to look for A13. A13 gets input from 3 fellows. One is the bias unit. One is not from X1, X2. X1, X2 are already processed. X1 or X2 are already processed and it goes on to an intermediate layer. Now we have got A12 and A22. Therefore, A13 gets information from the previous layer. So that is why A13 will get information from the second layer. So the third layer will get information from the second layer. So all the fellows which are giving inputs for the third layer will have a superscript 2. Is that clear? So A13 will get, and this drishti or whatever is your bias unit. That will be there. So the weight from the bias unit to A13 is W01 at the level 2, superscript 2. And A12, the weight is W112. And the bottom neuron, A22, is W212. So now, come after the third layer, come to the blue. The output Y1 is basically getting information again from 3 neurons. One is the bias unit, one is now A13, and the bottom is A23. And all the weights will have a superscript 3 now. W013 from the bias, W113 from the A13 neuron, and W213 from the bottom neuron. So this is the basic notation. This is how you start out with any neural network before you get into the mathematics. Fine? Okay. Now the question is, Baki, I'm not able to see. Just read the question. I can't see the title.
Question: if all the weights are initialized with 1.
No. Top. I can read the bottom. Top. What is the title slide?
Output of a single neuron.
Output of a single neuron. Okay, the output of a single neuron. So now, if all the weights are initialized with 1, what is the output of the highlighted neuron? Very simple, elementary. It's a quiz question. So 0.1, 0.2, 0.3, all the weights are 1. Now the answer is, we should not forget the bias unit. That is why this question, you may think it is a trivial question. The first thing is to put the bias. Once you put the bias, then you say it is linear. Let us say it is linear. Okay. So it is a linear combination of all the inputs. Z is Z is sigma Wi xi. So it is nothing but W naught x naught plus W1 x1 plus W2 x2 plus W3 x3. Please note that the bias will always see this anyway it will give 1 into 1. Plus you do all that. So you're getting a value of 1 into 0.1 plus 1 into 0.2 plus 1 into 0.2, which is 0.6 plus 1, it is 1.6. Now let us say that it is riding on a logistic. Then the A12, if it is riding on a logistic, then G of Z, which we are declaring. So the training function is sigmoidal. Then after you process all the inputs, that is the black and the 3 orange, calculate the Z or the Z. Now G of Z is basically whatever it is, 0.83. So the value of the neuron, maroon neuron A12 is 0.83. Okay. So this is the output of a neuron. Very good. Now what is the problem before us? What is the challenge? Given the y is an excess from the data, the challenge is to get a unique set of weights that minimize the error between the data and the ANN model. I come again. Given the y's, okay, given the y's or your data, it could be rainfall, it could be this thing, number of people getting heart attack, whatever will be your, and x is the controlling variable. So if it is heart attack or whatever, BP, sugar, obesity, this thing, you put whatever are your control variables down. You have a large data set from all the hospitals in the United States or India, whatever. You have a database. You've got age, you've got sex, you've got economic status, this thing, all that, smoking, drinking, this thing, all that. So you, whether they are doing exercise, not exercise, or they are not doing exercise, all these are excess. X1, X2, X3. Y's are basically they are getting or mild attack, severe attack, whatever. Okay. Now the challenge is to get a unique set of weights that minimize the error between the data and the ANN model. What is the ANN model? The ANN model will give a predictive relationship for y. Given x1 to xn, it will return the value of y. How can it do that? Because it is looking at this data, it is looking at your ANN architecture, it is looking at all the weights you have created, it gets trained, all the weights are given numbers. Therefore, once all the lights are switched on, I mean all the weights are trained, given the excess, it will be able to give the y. So this is the fundamental problem in ANN, and it is known as the training phase. Once the training phase is done, what is normally done, you won't leave the neural network into the open this thing and allow it to start predicting. There will be a validation or there will be a testing phase where you'll take a set of data. You'll take some other people who have heart attack, but who have all the variables, but this model has not seen those data. Then you will see the performance of the model. Then you can give R squared, correlation coefficient, whatever. And once it is reasonable, then you let this model out. Now, suppose the model starts not predicting properly, what we do is, even those points we include and retrain it so that you can train the weights. So dynamically, you can update the weights as and when you get more and more data. There is no finality. Okay, somebody is a big shot. He said it, and for 200 years, it won't change. So that is, so the beauty of data science, it is not like that. So there is a quotation, there is a saying by one statistics professor, like, if in God we trust, but all other people have to bring data. So we trust nobody, we trust only the data, assuming that the data is of good quality. Now, as and when new data comes, we can refine the model, we can have more hidden layers, we can have more neurons, you can change the weights, okay, or you can separate two networks. You can have two separate networks or multiple networks depending on Asia. There will be one network. For Europe, there will be one network. Africa, there will be. You will do whatever. For men, there will be one network. All that will come only as you keep working deeper and deeper into this problem. Now, simple question is quiz question. How many neurons are there in this network? Okay, how many neurons are there in the network? XA1. So okay. Now, you should never forget the bias unit. Okay. Of course, for the output layer, there is no bias unit. So you can see that input neurons are 2 input neurons, 3 in the hidden layer, and 1 output neuron. So the answer to the question is 6 neurons. So we run a course, okay, on inverse methods, me and Balaji Srinivasan in IIT Madras. So the last 10 lectures are based on neural network. We ask these questions for IIT students. How many? Many people, can you believe that many people get this wrong? So it's a 4-mark question. Many people say it is 4. If it is 4, why will we ask? It is a first standard question. No, why will we ask? So it is not 4. So you should think counterintuitively. When Prof is asking such a question, the first thing is the answer is not 4. That is the way you have to think. All right. Okay. Now, how many weights are there in this neural network? Next question. How many weights are there in this neural network? Now you can see I'm connecting the bias with the first neuron, second neuron. Don't connect the bias with the bias. I mean, that is illegal. Okay. Now, if you see all the arrows, 4 weights connecting input layer to the hidden layer, 3 weights connecting the hidden layer to the output layer. So there are 7 weights. Now, how do we get the 7 weights? For 20 values of X, if I get the 20 values of Y, I'll be able to minimize. So I will keep on guessing the values of W till I get a minimum error between the Y predicted and the Y data. So this is easier said than done. If there are multiple layers with multiple neurons, there should be a systematic way of doing this. Okay. So therefore, you can see that the determination of weights to minimize the error between the data and the model turns out to be an optimization problem. Therefore, at the heart of neural network, at the heart of an ANN, is optimization. Okay. The Desi way of doing it would be take 20 values of W1, to take 20 values of each of these weights and 20 into 20 into 20, but it is unimaginative and it is inefficient. This is not the way to do it. So you can say that you can computationally, I have enough computing power, I will just kill the problem by keep on exhaustively working out. But that will happen only when you are super duper rich, when you have powerful computing resources. But let me tell you why the field of optimization will not go, because the problem of the day, it has been seen last 50 years, the problem of the day is much tougher than the computer of the day. Therefore, some experts, some professors, some scientists, somebody who is specializing in machine learning, neural network optimization will always be required, because we don't have infinite resources to waste on. It is a very unimaginative to do 1 lakh computation with different weights and finding out just the 7 weights. There should be a smarter way of doing that, and many smart ways are available to do that. All right. Now, what is the title slide again? How to remove this? Okay. Now let us consider the question before us is now find the output of the network given x equal to 0.5. Okay. The training function is sigmoid. The 7 weights are given. Okay. The 7 weights are given to you. Please note that the blue color is basically from the hidden layer to the output layer. All right. The training function is sigmoid. So is the question clear to us? Now, who is giving me the weights and all that? Don't. See, it's an elementary question. It's a quiz question. Okay. So now we will see how to train it in a little while. Now, given this situation, what is the output? Okay. Now, Z1 square, not Z1 square. Z12 is basically, please note there is a catch here. The training function is sigmoid. Okay. So W01, 1 x0 plus W11 x1, which is 1 into 1 plus 0.7 into 0.5. So Z12 is 1.35. Is that clear? Can somebody say yes? Is it clear?
Yes, sir.
Okay. Okay. That A12, please note that A12 is not Z12, huh? Because the training function is not linear. Huh? Watch out, watch out, watch out. Training function is sigmoid. Okay. Therefore, A12 is the logistic riding on the Z12. That is 1.35. Therefore, A12, the value of the neuron is 0.7941. Like that, you can find out from all, you can also, the rest follows. Okay. Z2 to the Z22 is 0.8 into 1 plus 0.8 into 0.5, it's 1.25. A22 is G on 1.25, which is 0.773. So if you continue further, Z1 of 3 is basically the linear combination of all the blue weights plus the bias plus A12, A22. Now finally, you don't again write it on the sigmoid because usually it's a linear. So usually A13 equal to Z13, which is equal to Y. Unless we are specify that is also sigmoid. The last one, we don't torture it. It's a linear combination of all the previous this thing. So now that's how we set the problem. Therefore, given these 7 weights and given that the value of x is 0.5, the output is 2.225. But now this is an elementary problem, a very simple problem. The challenge before us is I am having various values of y for various values of x. Can you tell me what those w's are? That is the challenge before us. Okay. Okay. So what did we do so far? So far we have constructed neural network which acts as what is called as a forward model. Forward model is basically from input we are going to the output. Okay. If you are going from the input to the output, what you are assumed is all the weights are known. But the challenge before us is the input is also known, the output is also known, but we don't know what are the weights connecting this. So actually what confronts us, the problem in front of us is basically an inverse problem. So the neural network is basically inverse problem. How? So therefore the main idea is to learn the parameters or rules which govern the neural network. Now how do we do this? In other words, to cut a long story short, how do we get the weights? So they will say, no, cut the crap, come to the point. How do we get the weights? So the question before is, how do I get the weights? All right. So what then is given? What is given is a set of outputs and a corresponding set of inputs, simply called data. So it is data driven. The neural network is data driven. Therefore, data science precedes machine learning, just like thermodynamics and fluid mechanics have to precede heat transfer. Much in a similar way, data or data science precedes machine learning. All right. Now, we have already seen this view graph before. For the sake of completeness, I'll go through this again. So, given various values of x and a set of weights, if a neural network is trained, what it will do is it will return the value of y hat, which is the hypothesis. And now you have to compare it with the ground truth. Okay. The difference between these two in a least square sense is basically the cost function or the loss function j, which is a function of y, the y data, comma the y hat, which is your proposal. Now, the challenge before you is to do a feedback. What is that? The orange color comes back. I will keep on changing the w till such time the neural network does it right. Therefore, j comes to as low as a value as possible. Therefore, minimizing j is tantamount to solving a minimization problem or an optimization problem. Therefore, the construction of a neural network, which means the determination of weights, is simply an optimization problem. Is it okay? So, to learn the neural network parameters, we follow the following process. Create a neural network, propose a neural network architecture. What is that architecture? Input, output, this thing, whatever, how many hidden layers, whatever you decide. For an arbitrary, now you start guessing the weights W from the as many weights there are, so many guesses you have to make. So you make a guess for all the weights. Then we will get some output of the neural network, which anyway will not match the ground truth unless you are a super duper Swamiji, the first level itself. So the first shot itself, iteration, you get all the weights right, which is highly unlikely. That means you have copied from somebody, right? Okay. So I'm just kidding. Cool. So now you define a cost function depending on the difference. Find the optimal weight by minimizing JW, which is the feedback process. Now comes a fundamental trick which is applied by the machine learning expert, which is called the back propagation, which is outside the field of statistics. This back propagation is core to the neural network because it beats the idea of this J by, it beats it hands down because the machine learning experts have a very efficient way of solving this optimization problem by calculating the Jacobian. What is a Jacobian? So the Jacobian is basically so it's basically the partial of the cost divided by the partial of the weight. Okay, dou J by dou W. Okay, all right. Now we again use the gradient descent. I already taught you the gradient descent, but now watch it. We build a cost function with a large number of variables, and the objective is to adjust the parameters to see if the cost function is coming down to minimum. We iterate through various parameters, moving the direction of the maximum change, the gradient, and evaluate the cost function. Whenever we achieve a low cost function, which is desirable or agreeable, we conclude that the parameter state at that state gives the best fit to the model, then we stop. Okay. So this loss function, your J could be 10 to the minus 5, 10 to the minus 7, 10 to the minus 9, what have you. Okay. So this is the essence of gradient descent. So we can actually stop the lecture and say, okay, fine, I've done it. But you would have missed the point because there is a particular technique called backpropagation, which is at the heart of machine learning or neural network, which you will have to learn. Okay. Otherwise, calculating this is a very cumbersome process. Okay. So the gradient descent says that please note that W is a vector. W of I plus 1 is W of I because W has got so many components. W of I plus 1, the I plus 1 iteration is W of I minus alpha, where alpha is the learning rate into the partial of the cost divided by the partial of the I. Now, so you can do that with respect to the individual weights and so on. Finally, it will become a matrix. And so it becomes an exercise in linear algebra and so on. So that is the way you proceed. Now, consider a neural network like this. There are various blocks. So these F1, F2, F3 are intermediate layers and this thing, right, where you set up the day 1, 2, A2, 3, blah, 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 and all that. So given the set of weights, so you're calculating F1, F2, F3, Fn. Finally, you calculate the cost, JW. In such cases, the expression for the cost function exists as a composition of various functions. So many functions in between because there are too many weights, which is too complicated to formulate. And In between these weights, there could be a logistic or a tan H or a rectilinear function G of Z. So the G need not be always the logistic. Logistic, at least it's easy to evaluate the derivatives. Okay. So there could be a mess. So therefore, there should be a simpler way of doing this. Okay. So we do not have explicit expressions for gradient in such cases. So the gradient has to be numerically evaluated. So it becomes again comes to the domain of optimization. So even for a simple network with one hidden layer, finding the analytical expression for the gradient can be exceedingly tough. Okay. Since the J is a result of a chain, F of G of H of K of L of this thing, one can use what is called AD. AD is a very important tool in machine learning. So automatic differentiation to calculate the gradient. So I'll explain what AD is in a jiffy. For neural network, the equivalent method is back propagation. So back propagation, BP, not British Petroleum. So this holds the key, the back propagation. All right. Now, okay. Now let us explain back propagation, how back propagation works using a simple neural network. Now please look at what I've indicated in yellow color. One input layer, two hidden layers, one output layer. There is only one variable X in the input and there is only one Y hat in the one output layer. Now, so you can see that from X, there is a A1 and then there is a connection W1. Then it becomes Z of 2. I hope you're able to follow. So I'll move the cursor from A1, W1, you go to Z of 2. Then you put the activation function becomes A of 2. Then put a W2, it becomes Z of 3, then G A of 3, then W3, Z of 4, and then A of 4. And then finally you get the Y hat. Okay. Please remember, the superscript denotes the layer index. Okay, layer index. So 1, 2, 3, 4, not the node index. Now, Z superscript 2 is A1. Z superscript 2 is nothing but A1 multiplied by W1. Okay. Now, Z of 3 is A2 multiplied by W2. Z4 is A3 multiplied by W3. So the A of 2 is nothing but G of Z of 2. Z of 2 is A1 W1. You can see that. So you can see A of 3 will have G of A1, A2. So it will start from A1 on the right hand side. So it will be bracket within bracket within bracket. You can keep on doing it. Now, finally, the Y hat is A of 4, which is G of Z of 4. Z of 4 itself expression is given here. Now the cost function is basically half of Y minus Y hat whole square. Now the challenge before us is to evaluate the Jacobian. So the Jacobian is basically consists of here, there are only 3 weights. So we made it simple. There are only 3 weights. So the evaluating the Jacobian means in this case, I want to evaluate dou J by dou W1, dou J by dou W2. In this example, okay. Now the activation function. So Z of 2 is basically so now go to the right side. The activation function of the last layer can be either sigmoid or ReLU or tan H. However, in many applications, the last layer is chosen to have no activation function so that we have a linear output. In such cases, A of 4 equal to Z of 4 equal to Y. Okay, the left hand side is basically, don't worry, left hand side is what I already wrote. Okay, now, as the name itself indicates in back propagation, the gradients are evaluated in the reverse order. So what you do is, so you evaluate the gradients in the reverse order. So you evaluate the gradient here. From this you go here. From here you go here and then you go. So that is why it is called a back propagation. Okay. Now let us see. So once I explain for the first one, you'll get a hang of it. It will become very clear. Now, dou J of dou Z4 is nothing but dou J of dou A4 into dou A by dou Z. So I'm just using the chain rule, nothing else. Okay. Now dou J of dou A4 is nothing but half of Y minus Y hat whole square is 2 into Y minus Y bar, and 2 and 2 will get cancelled. And in this case, since A equal to Z equal to Y, dou A by dou Z equal to 1. Therefore, dou A by dou is equal to 1. and the dou j by dou equal to y bar minus y. Okay, because it's a differential of half of the error square. So finally, this I call it as a delta. Delta is a notation used by machine learning in neural network. So this dou j by dou z4 is put in terms of del to the 4. That means it is a layer 4. Okay. Up to this stage, is it okay? If you understood up to this stage, then it's just 5 minutes. I can go through other things. Can somebody endorse? You're able to follow? I hope it's not going above your head. All right.
Yes, sir.
Can someone? It's fine.
It's fine, sir. Yeah.
Very good. Okay. All right. Now come to A3. So from A3, there is a weight W3 which is taking it on to Z4. Therefore, dou j by dou W, I'm looking at here. Dou j by dou W3 is basically dou j by dou A4 into dou A4 by dou Z4 into dou Z4 by dou W3. Okay. But now whatever is indicated in the bracket is already done. Okay. It is already done. As dou j by dou Z4 is already del 4. Okay. So dou j by dou W3 is nothing but del 4 into dou Z4 by dou W3 is dou Z4 by dou A3 is nothing but by dou Z4 by dou W3 is nothing but A3. Okay. I come again, dou Z4 divided by dou W3 is nothing but A. Therefore, del 4 into A3. Therefore, dou j by dou W of L is delta of L plus 1 into A of L. So this is the back pocket. This is it. This is the fundamental trick. This is the fundamental trick of neural network. So the dou j by dou W of a particular station L is del of L plus 1 into A of L. Okay. If you know del of L plus 1, we can find dou j by dou W of L. And the last, and it is very easy to get the last delta because the last delta is linear. It is just a cost function. Therefore, you start from the right hand side from the output layer, del 4 to del 3. So you can first calculate all the dels, del 4, del 3, del 2, del 1 and all that. And then use this relation to calculate all the Jacobian. Once you calculate the Jacobian, what is the big deal? You just use this. W of I plus 1 is W of I minus alpha dou j by dou Wi. That's it. Alpha, what is the learning rate? You can put 0.5, 0.2, or you can use the Cauchy's method where you can actually make it as a single variable problem in alpha in one shot, get the value of alpha and proceed. This is also right. Okay. Now del 4. Now, if we know del of L plus 1, we know dou j, we can find dou j by dou WL. Okay. Now, can we relate del of L plus 1 and del of L? Let's find out by considering previous layer. So now the dou j by dou Z3 is dou j by dou Z4 into dou Z4 by dou A3 into dou A3 is just, we are playing with the chain rule. Therefore, del of 3 equal to del of 4 into W of 3 into G dash of. So dou A by dou J. In the previous layers, there is a G dash which comes because it is riding on a sigmoid. The last layer, the G dash did not come because the output was a linear. The previous layers, it is riding on a sigmoidal function. Therefore, it is G dash of Z of 3. Therefore, del of L is nothing but del of L plus 1 into W of L into G dash of Z of L if sigmoid is your training function. Okay. G dash of Z of L is nothing but the derivative of the activation function, which is straightforward to calculate. We've already done it in our previous classes when we did logistic regression. Okay. So derivative of the sigmoid function G of Z equal to G of Z into 1 minus G of Z. Similarly, the derivatives of other activation functions can also be found out. Okay. Now, please note this is your Bible. Okay. This is your sutra. Okay. Initialize the random weights. Through the forward pass, calculate Z of L plus 1 equal to WL of AL, and A of L plus 1 is G of Z of L plus 1 for all the layers. Evaluate the Y bar. Evaluate the Y hat. Okay. So I will tell you in a language in which you usually understand. You have a set of inputs. Now you randomize all the weights and then go from the input layer to the output layer. Get the values of Y, Y1, Y2, Y3. There are 100 data points, Y100. Okay. Now calculate the delta of the last layer as Y bar minus Y. Calculate the delta of the remaining layers using this, whatever we saw in the backward direction. Evaluate the gradients like what we did in the previous last 10 minutes. Update the weights using the gradient descent. Continue the procedure till the norm of the weights, till your error. Where is your function? Okay. So this must be done in a least square set. There are many points. Okay. Till the norm is less than a pre-designed. Okay. Now let us learn back. So I don't want to stretch to the next class, please. So otherwise you will forget. So just please put up with me for another 10 minutes, 10 or 12 minutes. We'll complete this example. Now I know that there's a lot of math in today's class. So, but if you go back tonight or tomorrow, sit with your calculator and paper and pencil and rework, you'll be able to get what I have said. If there is some doubt, if there is some gut butt, if there is some problem, please send me a mail. Okay. Now let us learn back propagation through an example with the help of hand. Now the same. There is one input X. There are only A1, 2. There is one hidden layer with 2 neurons, and then there is a final output layer A1 of 3. Finally, it is we are putting a linear function. Now from the previous calculations, please remember this is basically coming from slide number 19 and 20. We already done Z12, Z12, Z22, and Z11. Now calculate the weights after one iteration with alpha equal to 0.5. So we are actually doing the back propagation with hand instead of going to the computer, so that the learning is complete. Your learning is complete. Now let's say X equal to 0.5, Y equal to 0.5 with the following initial weights. Okay. As you know, so please remember, this is the question where we said how many weights are there. There are 7 weights in the problem, and the output layer weights are all given in terms blue color, and all the other weights are given black color. Okay. Now from the previous calculation, slides 19 and 20, we know Z12, Z22, Z13, A13, and Y. The cost function is basically, we already got, so the value you're getting is 2.225, Y. The data of Y is 0.5. Therefore, the error is now this one. The error is this. The error is now 1.54. The challenge is you should keep changing the weights such that this J comes down to as minimum as possible. That is the problem of the neural network training. All right. Now, dou J by dou Z3 is equal to delta. So you know that for the last one, it is nothing but you take the derivative of this 2 by 2 into Y bar minus Y. So it is just, so 2 and 2 will get cancelled. So it is just Y bar minus Y. So dou J by dou Z3 is nothing but 1.755. Now dou J by dou W2 equal to delta 3, that is the last layer, output layer, into A2. Okay. Please note now, A is a column vector. A is a column vector. What is A is a column vector? It consists of 3, the bias unit 1, A12, and A22. Okay. Therefore, A21, A12, A22 into del 3 is nothing but 1 plus, we already calculated this, 0.79, 0.773 into 1.75. Sir, where did you get this 1.75? I just got the 1.75 previously. Okay. I am no mumbo jumbo. I am not doing any magic. I am not doing any cheating. Plain math. Okay. So therefore, dou J by dou W2 is basically turned out to be 1.755, 1.39, 1.3645. Done. So now we have come up to dou J by dou W2. We did dou J by dou W3. W2 is done. Now we have to go to W1. Okay. Now, from the previous calculation, we already got the dou J by dou Z2 is del 2. Now we use the back propagation. Del of 2, then this is nothing but del of 3 into W of 2 into G of Z2 into, what is the G of Z2 into 1 minus G of Z2? Because that is a derivative of the sigmoidal function. Okay. Now, please remember that Z12 and Z22 are connected only by W11, W112. Okay. W112 and W212. Okay. All right. Now del 2 is nothing but your error into del 3 into 0.72 and all that math you do, and finally you're getting del 2 is 0.2 and 0.2735. Okay. Now dou J by dou W1 is del 2 into A1. Since W of 1 is a 2 by 2 matrix and A is the input layer which is connected by, A is also having A1. Okay. A1 is this layer. A1 is a column vector 1 by 2. So this will be 2 by 2 into 1 by 2. Finally, it will become a 2 by 2. Let's see that. Now, so dou J by dou W1 is a 2 by 2. Dou J divided by dou W011, dou J by dou W021, dou J by dou W11, dou J by dou W112. And you can do this. And okay. How are you getting this 1 and 0.5? How are you getting this 1 and 0.5? 1 is the bias unit and x is equal to 0.5 given. So, okay. That's how you're getting 1, 1 and 0.5, 0.5. Del 1 of 2, we already know previously. Okay. Now, if you do that, you are getting this Jacobian for the first weight as this square matrix. Now, through the gradient descent, so W of 2 equal to W of 2 minus alpha. So you can get the new weights using this learning function. Now we assume that the problem I've initially given to you that the learning rate is 0.5. Okay. Now, if you do that, you can also calculate W1, right? Now, with this, you can also calculate W01, 1, W01, 2, W1, and now we are calculating all the weights after the first iteration. All right. So now, finally, the weights are all updated after one iteration. With the new weights, we estimate the forward model and we get the cost function. We repeat this procedure until the error comes to below a certain value. Okay. The ANN converged at the end of fourth iteration. So 0.5, 0.5, 0.5 is the Y for all the 5 iterations. The Y bar goes from 2.25 point. It is oscillating, and finally at the end of the fourth or fifth iteration becomes 0.5. The cost function becomes 5.70 in 10 to the power of 1. Now, how does a final neural network look like? Yes, this is the final answer. The final neural network is, if there is a bias unit of 1, if x is 0.5 with all these connections, intermediate neurons will give you 1.2245, 1.08. Sir, what is that 0.778? Don't worry. G of 1.22 is 0.77. G of 1.08 is 0.77. And then there are 3 blue weights, 0.22, 0.07, 0.294. If you do that, you get a 0.4. And then it is linear. The G of Z is again 0.5 because you are not using the log sigmoid. You're using a linear this thing. Therefore, you get a 0.5. Now, the challenge is, instead of one value of the orange 0.5, if you have 100 values, you can get 100 values of the output. Instead of one variable, you're having several quantities, x1, x2, x3, x4, and y is also a vector. Then it will be very useful to do that. So now non-linearities are captured by having more than one hidden layer and also by using different activation functions. Okay. This is the feed forward back propagation neural network. All right. So that's it. So I think we have learned something important today. So any questions, you can please ask me. So I hope it was too fast. Any comments? So this is how. So now, if you use a MATLAB toolbox, it will do it for you. You don't have, but it is good, always good to know this, because you know that it is not mumbo jumbo. It is for a simple problem. It is possible for you to do it. Ask this MATLAB to do whatever, ask him to do what you want it to do, and check whether it is actually doing what you want him to do. Okay. Then the learning becomes complete. So you'll have faith in whatever toolbox you're using, the neural network is fine. So now you can do it apply in many fields. Okay. You can use it for solving it. You can use it for getting patterns, looking at patterns. Computer science people are doing it for all sorts of things. All right. Okay. So any questions? So was it okay? It's a little bit heavy, but I think. Yeah, any feedback? It's all fine?
Yes, sir.
Okay. Srikanth, are you still there?
Yes, sir. I'm still there.
So you can say hi to Professor Jayesh. He's there.
Oh, hi, Professor.
Okay. All right. Okay. Baki Harish, thanks for all the slides. Okay. So for all the hard work.
Yes, sir. Thank you.
All right. Okay. So thank you. So next class, we are going to take 2 examples. First is the Marshall-Palmer distribution. Marshall-Palmer distribution, which is connecting the rain rate with reflectivity. That we will do using the backpropagation neural network. And the second example will be, basically, we will look at the classification problem of stratiform and convective. So stratiform and convective, which we solve by logistic, we'll solve by neural network. And the last class on 12th April, we'll present the results of both Baki Harish and Sandeep's work on sensitivity analysis and calibration of numerical weather prediction model for better prediction of monsoon. So we are using heavy computing. Lots and lots and thousands of cases are run, and we are using various types of forward models, sensitivity, and genetic algorithms. And so on. All right. Thank you very much. I'll call.
Balaji, I want to make an impertinent comment.
Sir.
For a black box model, where do you want to go through and do it analytically in the class? There is no need for it. It's a black box anyway.
No, but many people think that it is mumbo jumbo. It is doing something. So
No, ultimately, when you look at the real problem, it's a mumbo jumbo. You don't know what it is doing. The real problem.
No,
See,
it is doing just more of this, except that you cannot do it with hands, sir. That's all.
No, but I'll tell you, when you're using Sigmoid function and so on, and nonlinear function, you cannot figure it out anyway.
No, for toy problems we can figure it out, sir. For actual problems,
But that doesn't help you to figure out what happened in the real problem.
So it gives you peace of mind. So
I would rather you give examples in which you do it by neural network and some of the method and show how much better neural network is. That's what I would like to see.
Yeah, that we will do, sir. The last class we will do that. Next class we will do two examples. The last class we will do that.
Sir, I want to make a note that the next class will be Python codes of the two problems.
Python code. We'll give the Python.
Balaji sir just now mentioned Python codes of linear regression with Marshall-Plummer distribution, and another one with logistic regression of precipitation classification. Those codes and like ANN, real ANN, will show them in the next class.
In the next class, in the final class, we'll show a real big ANN, which we cannot do it with this. So we see, because we are coming from engineering background. So sir, why if we straight away go to that, people will think that we are doing some mumbo jumbo. A lot of people have that. That is why I wanted to make it clear to the people.
But you cannot say when you're using all the nonlinear functions, you really cannot do anything analytically, right? It's not possible.
So but that is not possible, but we have to believe it.
And the power of NN is for nonlinear problems, not for linear problems.
Correct. Of course.
This might make people feel comfortable that this is similar to what they do in linear regression or something. It may give them some confidence, but really when the real problem comes, I don't think we can figure out how it did it. That's the nature of all black box approaches.
So you have to just get awestruck. That's all that it is doing.
But what I want is, whenever black box approaches are discussed, I would like examples where it fails, examples where it works, and that's what I think is real thing you can show.
So
where it fails.
Where it works, we can show, sir. Where it fails, we'll think, sir. So if it's possible, we'll include some example. For example, if you're trying to solve Navier-Stokes equation, it is failing. That we have seen. For some cases, it really fails. So and if you take correlated variables, it will fail and so on. So there are cases where it doesn't do well. So
so to me, some examples of what, because people, once you have the black box method, sometimes people will misuse it because they don't know.
They'll also get carried away. They think it will solve anything and all that.
Right. Okay. Thank you.
Okay, sir. Thank you.